Chapter 9 looks at Lewis theory, and Lewis theory helps us to decide the shape and the polarity of molecules. This is helpful for lots of reasons, but one main one, or a big one that's important to your life, is that this determines if a molecule will fit into the active site of an enzyme or not, and if it will activate that enzyme in your body to carry out a particular process. As always, there's some suggested problems for you to work on to make sure that you understand the material presented in this problem. The answer to the odd problems are found at the end of the book. When we draw Lewis structures of atoms, we need to focus on the valence electrons. Valence electrons are important because they are what determines the bonding and how the element bonds. And so we do draw them, the valence electrons, as dots surrounding the symbol for the element. So these are also known as electron dot structures or Lewis structures. The symbol in the center, the symbol of the element, represents the nucleus and all of our core electrons. The dots around the outside are our valence electrons, and we put 2 dots first to represent the filling of the s orbital, and then 1 dot on each of the open sides. So we're drawing them as a box. So if we have our element, you can kind of think of it as if it's in a box. We draw 2 electrons first to represent the s orbital, and then however many electrons are past that, we start filling around the outside of the box. So this is a square representation of our orbital diagram. So some examples you can see at the bottom. So we've got lithium, beryllium, boron, carbon, and as we move across the row of the periodic table, this would be row 2, we're adding electrons into that valence shell till we get to neon, which is our noble gas and has a complete s and p. They have full s and p orbitals. So here's a practice for you. Write the Lewis structure for arsenic. Arsenic has 5 valence electrons, and so therefore we write arsenic in the center. The AS is our abbreviation, and then we put 2 electrons paired on one side, and then 1 on each of the following sides. It does not matter which side you put the paired electrons on, just as long as you have 1 set that are paired and 3 that are unpaired. Because we're focusing on valence electrons, atoms want to share or steal electrons in order to get 8 valence electrons. We call this the Octet Rule. They want to have the electron configuration of a noble gas, which consists of a full s and a full p orbital, no matter what row that they're in. There are some exceptions to this, however. So hydrogen wants to behave like helium, so it is only going to form 1 bond. Our lithium is going to lose electrons so that it can become like helium. So it's going to make ionic bonds, and it's going to only have 2 electrons, or prefer 2 electrons. Beryllium likes to make 2 bonds because of its 2 electrons in its Lewis structure, and boron likes to make 3 bonds. So these are exceptions to the Octet Rule. They're going to want to attain an electron configuration like helium. We do also have the case where if we are in period 3 or below, so row 3 or below, we can have an expanded octet, so more than 8 electrons. We can actually have the case where we have 10 or 12 electrons. And the reason we can do this is because there are empty d orbitals. Because we're in row 3, we have the s orbital, the p orbital, and although there aren't any electrons in it, there does exist a d orbital. So if it's in row 3 or below, we can put extra electrons into that d orbital. So let's look at when we start making covalent bonds. Lewis structures can be used for valence or for ionic bonds, but covalent bonds are much more common. So we have things called bonding and lone pair electrons. So if the electrons are drawn between atoms, that means that they are sharing those electrons. And those would be the bonding electrons or bonding pairs. We typically draw those bonding pairs as lines representing the bonds. Electrons that are not shared by atoms, so they are located only on one element, those are what we call lone pairs or non-bonding pairs. So in our example, the dots that are drawn between the sulfur and the oxygens are bonding pairs. The dots that are drawn specifically on sulfur or oxygen are lone pairs. So we have quite a few lone pairs in this particular molecule. We have 1, 2, 3, 4, 5, 6 lone pairs, and we have 3 bonding pairs. This would result in a single bond between sulfur and oxygen on the right-hand side, and a double bond between the sulfur and oxygen on the left-hand side. And it doesn't matter where you would draw that double bond or that